A horizontal plane supports a stationary vertical cylinder of radius r, and the disk A is attached to a cylinder by a horizontal thread of length L0. And here's a picture of that. An initial velocity v0 is imparted to the disk as shown in the figure. How long will it take? How long will it move along the plane until it strikes against the cylinder? There is no friction. So I've taken this from the book called Irodov. It's a nice book. And so this is the problem, and here's a picture of that, and here is the trajectory of the particle as it will rotate around. So if this, right somewhere here, so if this is the cylinder and this is that particle, it has a velocity v0. Okay, so let's consider that after a certain time t, it is in such position like so, and it still has its horizontal velocity v0, right? So this is 90 degrees, and let's say that this angle is theta, and what I'm going to do is I'm going to move a further angle of d theta. So the string will look something like this, right? And d theta is infinitesimally small, and it has this velocity here v0. Okay, now the initial length of this string is L0. So after it has covered and the radius of this cylinder is r, right? So this is r. So after it covers an angle of theta in the cylinder, how much of the string is left now? The string left will be L0 minus this arc length, right? This arc length right here, and that arc length will be r theta if theta is measured in radians. So yeah, so that is the left out string. And now so this is r theta, right? Leave it like that. Okay, so now after the time dt, it covers an angle of d theta, right? So what is actually yeah, so this angle is theta. So what is this angle going to be? Well, that angle is also d theta, that angle right there, that will be d theta, and that is because if this is a circle and there are two tangents like this, sorry, two radii like this, and if this is the tangent for the first radii and this is the tangent of the second radii, then you can say that this angle is equal to this angle. That is the angle between the radii is equal to the angle between their respective tangents. Okay, so that angle is also d theta. So how much is this arc length then? This arc length, I'll call that dl. That dl is going to be you can consider this to be an arc of a circle, as long as the d theta is very small and we are going an infinitesimally small time. So how much is dl? dl is going to be is this distance, this length of the string which is left out. We know what it is. I'll just call it L. So this is L. So that is L times d theta, right? L times d theta, so that is the arc length dl, but that is also equal to L, which is L0 minus r theta, right? Oh sorry, yeah, so dl is going to be L0 minus r theta times d theta, all of that times d theta. Okay, so how much is this, how much, let me write it down here. How much time does it take to cover dl? How much time does it take to cover dl? Well, dl is the distance and v0 is the velocity, so we know that distance is speed into time, distance is dl, speed is v0, and time is a small time dt. So what is dt then? This implies that dt will be dl, but dl is this L0 minus r theta d theta over dt. Okay, so that is, oops, sorry, no dt. Yeah, so L0 minus r theta d theta over dl over dl. Let me check if that is right. It is dl by right. Oh shit, that is actually v0 here. Okay, so what I can do is I can integrate both sides now. I'll integrate both sides. Time goes from 0 to some time t, and theta goes from, initially the theta was 0, right? When this is here, this angle is 0, so theta goes from 0 to some angle theta. So what do we get here? What do we get? On the left hand side we have t. On the right hand side, if I pull this v0 out and I multiply both sides, then this becomes v0 t is equal to, if I integrate this, L0 minus r theta times d theta, I will get L0 theta minus r theta squared over 2, right? Okay, and this is a definite integral, so we don't need to worry about the constant of integration, right? So what they're not asking us how much time does it take to cover an angle theta, but they say that how much time does it take to until it strikes the cylinder, right? So we have to ask one question to ourselves: what angle does it make when it hits the cylinder? How much angle does it make? Well, that angle will be L0 times that angle times whatever angle, I'll call it alpha. That should be oh sorry, not L0 times alpha, but R times alpha. R times that angle alpha, which it will make when it hits the cylinder, should be equal to L0, right? Because when this covers fully, if that is the winding there, and if it makes an angle theta, then the radius times the theta will be the length of the arc, and that length of the arc will completely be L0 because it has covered the whole cylinder, right? So from here we get that alpha is L0 divided by R. So this becomes v0 t is equal to L0 times, now they asked us how much time does it take to cover this angle, right? How much time does it take to cover this much angle alpha? So we'll use this identity which we derived just now. So instead of theta, we'll write L0 divided by what is this, R. L0 divided by R. So this becomes L0 divided by R instead of theta, and R times R over 2 times L0 divided by R squared. So how much is it? B0 T is L0 squared over R minus L0 squared over 2R, right? So that is L0 squared over 2R. So how much is T then? T will be L0 squared divided by 2 B0 R. There you go. That is the time taken by the particle to cover a distance, to cover the whole cylinder, if these conditions are met which were given in the question. So yeah, that's pretty much it, and I'll see you in the next video.